Good morning, afternoon, or evening, everyone, and welcome back to the point distribution webinar. Today we have one of our organizers, Oleksandr Vlasiuk from Florida State University, talking about asymptotic properties of short-range interaction functionals. As a reminder, you are welcome to have your cameras on during the talk, so he's not just speaking to the void, but aren't required to. And after the talk and questions, there will be time left for just socialization if anyone wants to stay on. Alex, the floor is yours.
Great, thank you. Many thanks to the organizers and so on. What I will present is joint work with Doug Harden and Ed Seff, and so we'll be putting a preprint on arXiv about this project soon. So I want to start with a tale of two problems. Okay, in a true Dickensian fashion, I'll have to start from afar. So it's good that Stefan's talks preceded this one, because Stefan also talked about what is effectively optimal quantization, and so that's the problem I want to discuss first. So here is the problem. Suppose you're given a random variable C, right? It's has continuous distribution with respect to d-dimensional Lebesgue measure, and so C belongs to RD. And so the idea is you want to minimize over all functions that take at most n different values, this expression here, right? So what happens here is you're replacing some continuous random variable with this. So here f, say, acts from RD to RD, like so. Where is my pointer? And so what it does, it effectively discretizes the continuous signal C. So think about the following example. So you have some continuous signal, right? So you have maybe amplitude of some radio transmitter. So the transmitter is transmitting some signal, and you have the amplitude of the signal. So it's a continuous quantity, but continuous quantities are not good, okay? Because you cannot transmit continuous quantity without losses. So that's the problem. For continuous quantity, the losses are necessarily big. Whereas suppose you take this continuous signal X, right? So it takes, say, any real, it's a one-dimensional signal, it takes any real variable, any real value, and you replace it with only, 5 different possibilities, right? So this will be our quantizer. So f just replaces x with the y that corresponds to the part of the real line where x falls. So here SIs are just these intervals from -infinity to A1, A1, A2, and so on. And so if x falls in some interval, you just replace x with y sub I. You just say, okay, well, my x is then the y sub I. So this problem arises in signal processing. So just like I explained, you want to quantize a continuous signal so that then you can transmit the discrete version, right? And for the discrete version, you can use the error correcting codes, for example, right? So for the quantized version, you know that, well, whatever you transmit, if it's a little bit away from y0, it still must be y0, because these are the only values your discrete quantizers can take. And so that's the motivation behind this this problem, finding the optimal function, right, that quantizes this continuous signal in the best way. So you just want to look at the expectation of the error and make sure that it's minimal over all possible quantizers. Equivalently, you can state this problem as follows, right? So because you're always quantizing the signal x to yi, what you're doing is you're integrating over RD, over wherever your signal lives. You're integrating over RD this expression here with respect to the distribution of the random signal. And so this here is the optimal quantization problem. So for some reason, I don't see my pointer, so which doesn't make my handwriting any better. Okay, so now another equivalent statement to this one is to phrase it as approximating continuous measures with discrete measures. And this is exactly the same as Stefan already defined. So what we are doing here is we are looking at, we have some fixed continuous measure mu, and we approximate it with discrete measures nu. Right? So nu here lives in the space of probability measures supported on at most n points, right? So n is the number of values that your quantizer takes. And so the minimizer of this Wasserstein distance over all such nus is exactly the solution to the quantization problem. So if you know where to put discrete points so that the integral in the previous slide is minimized, then you also know that the probability measure supported on these discrete omega n's is the closest probability measure in Wasserstein p distance. So by the way, from now on, whenever we write omega n, we mean a discrete configuration. It has n points. The points are indexed, the points are denoted by xi's. All right, so these two are equivalent formulations. And so the optimal quantization statement, I think, came first. It came as I already explained in the information theory. The information theory community came up with it. And actually, this idea of quantization is already discussed in very old papers on signal compression. In particular, there's one by Oliver, Pierce, and Shannon from 1948, and it's great to have a topic started by Shannon. So anything that has Shannon's name on it is great automatically. I think we can all agree. So this has been studied in the following 3 decades through 80s. In particular, the asymptotic properties of the error were studied. So here we are looking again. So we have a fixed random variable xi. We know that it has a finite moment. So here, by the way, delta is something positive. So if you have a finite moment of order slightly bigger than the p, than the exponent you have in the optimal quantization error. So this guy here is called optimal quantization error. So I should probably say that without minimum, it's just the quantization error, and with minimum, it's the optimal quantization error. All right. So if you have a fixed random signal, right, and you know it has it's continuous with respect to the Lebesgue measure on RD, then you can study the asymptotics of this expression here. It turns out you can find the optimal order of the asymptotics, and here it is. So this is again exactly the same problem as Stefan described. So this corresponds to the set problem, right? This is the set problem, not the sequence problem that he looked at last week. And so you can compute this asymptotics up to some normalization constant. The constant, knowing the constant is very hard because you want to know exactly what the quantizer is, but you can also show that the expression for the asymptotic limit depends on the density somehow, and this is how it depends on the density. So here again, P is the exponent in the quantization error, or equivalently the exponent in Wasserstein distance that is being used. So this means already in the 80s it was shown that the set problem can be solved in the sense that the asymptotic order exists. So there were some more recent developments on this. So the most general result in this direction about the asymptotics of these functions has been established by Gruber, published in Advances in 2004. And so what Gruber does is he shows, well, he establishes this formula for random variables distributed on a smooth Riemann manifold. So his other achievement involves, so this is in a different paper, not the one in Advances, but he also shows, he obtains the value of the constant. So the value of this constant is only known for the two-dimensional case. So for two-dimensional manifolds, you know that this here is the pth moment of regular hexagon of area 1. So of course, this has to do with the fact that the solution to optimal quantization in 2D is hexagonal lattice. Okay, so for that reason, you can solve this in the sense you can even determine the constant. Now, in general, there is something called Gerscher's conjecture. So this is only known for D equals 2. Now, what if D is not 2? Well, then there is something called Gerscher's conjecture, still open. And what it says is that it is conjectured that the cell, the Voronoi cell of the optimal quantizer is asymptotically a polytope that tiles RD. Okay, so it is natural to explain that, natural to expect that maybe in dimension 24 it's going to be a Leech lattice, because, okay, well, it's at least locally optimal for covering. So there is something going on for it with respect to covering. Again, it's unlikely that E8 is going to be optimal because E8 is not best. It's not optimal for covering. Okay, and so this is the progress that has been made in the information theory community through the 80s. To the end of 80s. Then a little bit later, it was, so this problem, the optimal quantization, was popularized for its applications to generating distributions. So this has to do with, there was a nice review article by Du, Faber, and Gansberger, which explains how you use these how you use optimal quantizers for known distribution. And then, for example, this here is an approximate optimal quantizer for P equals 2. So in this picture, P equals 2. And so the case P equals 2 is also known as the case of centroidal Voronoi tessellations. And this is the most often used exponent for distributing points. So there is something called Lloyd's algorithm, which has been actually discovered much earlier than in the 90s, but then rediscovered many, many times. And so what it says is that, well, basically you just want to iterate. So you have a configuration, you tessellate the domain into Voronoi cells, you compute centroids of each cell, and then you move configuration to the position of these centroids and then repeat. So that's Lloyd's algorithm. And there has been some progress on the convergence of it and so on. And so that's partly what this review is about. So there are also some sort of fun illustrations of this principle in the animal kingdom. So animals like hexagonal lattice and so on. So at least they like minimizing quantization errors. So here are some fishes which partition the plane according to their hunting preferences, and so they sort of minimize some moment. So maybe the second moment, it's hard to tell from the picture. Okay, any questions so far to optimal quantization? Good. So this is the first part of the tale of two problems, right? The first problem is this optimal quantization. It's basically, you can think of it in terms of finding the closest discrete measure to a continuous measure if you use Wasserstein P distance. Now, another problem that has seemed unrelated is that of finding optimal configurations. Optimal meaning minimizing the Riesz interactions. So first of all, if you try to think about interactions with the Riesz kernel, this is the Riesz kernel, right? So this is what we call Riesz kernel, this guy here. So finding a measure that would minimize a functional like this when S is such that this kernel is integrable is difficult. Okay, so it's basically for the harmonic case, when this is the fundamental solution of the Laplacian, then it is known that this is harmonic measure, and studying harmonic measure is hard. There's an entire field of analysis that studies only harmonic measure, and there are other exponents. So it's pretty hard to find what is a measure that optimizes such a functional. Now, what you can do instead is study the case of large S, right? So this was small s. What we are going to do is to study interactions like this. Okay, so for the discrete, when you only look at the discrete configurations omega n, then you can make up sums like this. It doesn't matter what the exponent is because we're not taking interaction of a point with itself. And so it is meaningful to talk about what minimizes such interactions over omega n's. Now it is necessary in this case to take omega n in a compact set, right? So fix a compact set A, and then perform minimization of such a functional over all omega n's in this A. And so this is seemingly unrelated, right? So we are changing the problem quite a bit. It doesn't depend on the set anymore. So this, unlike the optimal quantization problem, there is no dependence on the set, right? There is no integration over A. It's just, we just look at pairs of points, look at these, evaluate kernels on these pairs, and that's it. And then there is some weight. Okay, so this guy here is the weight. So a final, the final word about weights. So from now on, whenever we say weights, we mean continuous weights. So there are some ways to circumvent this, but okay, whenever you see a weight, it's continuous. So what is the deal about large S? Well, unlike the case of small s, finding the measure that is asymptotically optimal somehow for this configuration is not that hard. Okay, so what is known about the asymptotics for large n of such discrete configurations is, well, quite a bit. Okay, so again, it is known that the asymptotics, so here the order is different from, just for comparison, for optimal quantizers, we had to multiply by n to the power p over d. Here we have to divide by this n to 1 plus s over d. But again, just like for optimal quantizers, what you can do is to show that the asymptotics depend on density of well, depend on the weight that you put in the release energy. And so this is the dependence. So now, superficially, it looks quite a bit similar, right? So you just take density, raise it to some power, and then, well, you take the inverse power outside the integral. So this is like some sort of norm of eta, and the norm is minus g over s, right? So it's some sort of averaging norm, but it's not a p norm, meaning p is not bigger than 1. It's not positive. It's some sort of negative p. But still, you can explicitly compute the limiting measure of optimal configurations, so of configurations that attain this minimum, and the limiting measure is proportional to this guy here. Okay, sorry, this actually shouldn't be h, this is eta as well. So the limiting measure is known, so just as it was for optimal quantizers, the limiting measure was also proportional to the expression under the integral. So in this case, when s is bigger than d, if you minimize the discrete functional, right, and then look at the limit of normalized counting measures, you can compute this limit. So the common feature of these two problems so far is that, hey, we can compute asymptotics, right, for both of them. By asymptotics, we mean both the limiting, both the asymptotics of the minimal values of the functional and the limiting measure of discrete configurations. And so you can do all, you can do a bunch of other tricks. You can, you know, in addition to putting a weight here, you can also, not only can put weight here, you can also add an external field and then compute the limiting measure in that case. And so life is good. Okay, so just like for optimal quantizers, you can compute things relatively easily compared to long-range problems, such as, say, for the harmonic kernel, where life is hard and the equilibrium measure is much harder to compute. So also, I've shown you, oops, sorry. I've shown you what the new optimal quantizers look like, and so they look quite nice. You have seen that the Voronoi cells are all pretty much hexagonal, and so they all look very good. And so the same is true for near optimal configurations of this hypersingular Riesz interaction, right? So if you minimize this guy, right, with s bigger than d, and say you do it on some manifold, restrict just to some sufficiently smooth set so you can minimize things. So what you see is, again, things look very nice locally. So the Voronoi cells, so if you do Voronoi tessellation of this surface, they look very much hexagonal. So again, a very nice local structure. And so, so these are the two problems, right? So the common features so far where, well, we can compute limiting measure, can compute asymptotics, and the expressions sort of look similar, right? So what's the reason for this similarity? So let's go to thinking about the way. So the reason we choose the s bigger than d exponent, right, is that for such exponent, short-range interactions dominate. So asymptotically, the first term of the asymptotic expansion corresponds to short-range interactions. And so what about, so how about we just drop everything that's not short range? Right? So how about we do what physicists do? So there are physicists, and being clever, some of the models that they consider involve only nearest neighbor interactions. Right? So the clever physicist says, I don't want a complicated model, I want a simple model. How would I construct a simple model of interaction in a configuration? Well, I'm just going to look at interaction with nearest neighbor, maybe with the nearest neighbor, or perhaps with several nearest neighbors. Okay. And so in other words, let's do this. Let's look at, again, we're going to sum up the Riese kernel, but now we're not looking at the complete n squared interaction, right, of every point with every other point. Let's just look at several nearest neighbors. And so we realized that the same asymptotic results hold, right? So meaning the same asymptotic results as in the case S bigger than D. Except that now, because you do this trick of truncating to the nearest neighbor, you don't care what S is. It just has to be positive. Actually, it doesn't even have to be positive, but that's slightly longer story. So basically, if you do the truncation to several nearest neighbors, you're good. You have the same result, the same asymptotic rate, except that now S is not necessarily bigger than D, just anything, and you get the same expression and so on. So there is really something that makes an interaction amenable to this sort of analysis, right? So we have done some analysis of the optimal quantizers, and then of S bigger than D, then of these truncated guys. And so in all these cases, we're getting suspiciously close expressions for the asymptotics, all right? And in all of these cases, we get suspiciously nice local structure. So this is the seminar, this is our webinar logo, right? So now I'm going full disclosure, what's going on in this logo. So you've been wondering, what is this logo? I wonder what is the ad for, right? Doesn't state clearly what's the company this ad is for. Now, what this ad is for is, it's an approximate minimizer of this nearest neighbor interaction. So you take several, for each point, you only look at several nearest neighbors, and that's all you count in this sum of Riese kernels. Right? And so you minimize this. What you end up with is something that looks nice. Again, in the sense, so I haven't quantized nice so far, but you can see that statistically, if you do Voronoi tessellation of this configuration on the surface, statistically everything is a hexagon. Right? So okay, so this color here means hexagon. The little orange and blue strips are heptagons and pentagons, and so only these several large guys have more sides than 7. I think they have 8. So light yellow means 8 sides in the Voronoi cell. So in all the 3 cases, and for all the 3 interactions, local structure is remarkably nice. So it's sort of very close to that Gersha conjecture in the sense that, well, at least when we know what the limiting Voronoi cells should be, it looks like indeed statistically the Voronoi cells are close to what we're expecting by Gersha. And so now, how do we generalize this? Right? So first of all, we still need to understand: did these expressions for the asymptotics, did they just look similar, or are they indeed the same somehow for optimal quantizers and these Riese interactions? So we try to understand what is common. Okay, so the common features are that, okay, well, first of all, we can compute things, and for the other interactions we cannot. Okay, so that's great, great heuristics. Now, apart from that, if you don't do any weight, right? If you don't add any weight to the interaction, then it's going to be scale invariant and translation invariant. So both for optimal quantizers and for these Riese interactions, if you just rescale the configuration and the domain, then minimizers are also rescaled. And similarly for translation, if you just translate your configuration around with the domain similarly, nothing changes, right? And the third feature, which Stefan, again, luckily, at some point Stefan mentioned this, which is kind of remarkable. So the remote parts of the configuration that you're looking at do not interact much. Meaning, if you are computing this, E sub s of omega n, or if you're computing, I guess I denoted this, m sub np of omega n. If you change the configuration locally, then, well, it's especially obvious if you do the k-nearest neighbor truncation, then the other part of the set doesn't know anything because it only looks at nearest neighbors. It's similar for the hypersingular case, it's just that the short-range interactions dominate. Okay. Now, for quantizers, similarly, if you perturb the density a little bit here, then the part of the set that's far away, it doesn't care. Okay, so they are all short-range. And so here is a beautiful, beautiful, very informative picture which illustrates this. Okay, so if you have nearest neighbor interactions, you only look at several nearest neighbors. If you are looking at optimal quantizers, then what are you doing? Well, what you're doing is you're summing up moments of Voronoi cells in the configuration. So say this is V sub I, right? This is my point, xi. I look at its Voronoi cell, and then what my quantization error is just the sum. So say I'm comparing, say there is no weight, I'm just comparing, I'm just trying to approximate the uniform measure. So then I'm just summing up moments of these Voronoi cells. Now, what defines a Voronoi cell is just several points which are again close nearby, right? So the sides of the Voronoi cell are just perpendicular lines to these segments connecting xi with the nearby points. So you just look at the neighboring Voronoi cells, and that's all that defines the form of the Voronoi cell. And so then we're going to try to formalize. Okay, so what's this about the short-rangeness of an interaction? So first of all, what kind of functionals we talk about? So we want to talk about anything that takes, collection of points and the set as arguments. It's going to be maybe semi-continuous so that you can minimize it. So we're going to talk about functionals. They take a function, they take a configuration omega n, and they take a set. Right? And sets are all going to come from some big universal set. So this is fixed and open. Right? So we have just some big omega. Everything comes from that omega. And so we want to study asymptotics. When does asymptotics exist? Right? So we have these configurations that extremize this Gothic E, right? So we have a functional, we have some extremizers to it. They can be minimizers, but they don't have to be. They can also be maximizers if we sort of flip the problem correctly. But the idea is somehow these are interesting configurations for this function. Okay. And then we want to study asymptotics. Now, I haven't said yet what the rate is, right? So rate is some reasonable function, so something that you'd expect to be a rate. But so far, we're not saying anything about this T of n. So we have seen previously that T of n has been always a power function in the three cases, in the three problems that we considered so far, or maybe two problems. In the two problems that we considered so far, it has always been a power function, right? And then another thing that we want to have for these E's, for these interaction functionals, is we want monotonicity in the set. Okay, so this makes sense if you think about minimizers, right? So if you make your set bigger, if you have A contained in B, then minimizing over a larger set gives you a smaller value. So we want some set monotonicity. So similarly for quantizers, if you try to approximate a continuous measure on a larger set, you get larger error. But there's also some monotonicity. And so if you make these assumptions, so you have functional, it's so say we talk about minimizers, then this has to be lower semi-continuous. And and there are these starred omega n that depend on the set. Right? So then we can study the asymptotics. We can show that it exists. So I know everyone loves theorems that take entire slides. So here's one. Okay. So basically what this says, and I'm going to doodle here because you're not going to want to read it, so I'm going to draw some pictures. So first of all, the preamble here says, well, you want that the rate is reasonable, right? So somehow the rate is asymptotically convex. So if you take this ratio of rate to itself, you get a convex function. You can also ask that this be concave if you're doing maximizers, but let's say this W of t. So this is a Gothic W, by the way. I get to show off my knowledge of fonts. So this is lowercase Gothic W. So there. And this is lowercase Gothic t. So great. This is very Gothic theorem. All right. So the limit for this rate is a convex function. Also, you ask that the limit on a cube, the asymptotics on a cube exists, whatever the cube is, right? So suppose you have, okay, I don't see my pointer, so this won't work very well. No matter what cube you're looking at, asymptotics on it must exist and depend only on the size of the cube. So in general, this is something that you're going to get if you have scale invariant interaction. Okay, so it's more or less the idea. So if it's scale invariant, expect that something like this is probably true. E also has to be short range, right? This is exactly what I said about different parts of the set not caring about each other. So if you have a set and you intersect it with a couple of cubes, all right, then we're going to ask that energy of E of the part of your configuration. So say we have configuration, it's everywhere in the set, right? And the idea is that for B, we're asking that E of so omega n that, oops. Okay, let me erase this because, okay, so E of omega n that intersects two cubes. Okay, it's rather hard to write if you don't see your own pointer. And so this has to be of the same order. So the asymptotics of ratio of this to E of omega n kept with Q1. Yeah, sorry about the terrible handwriting. For some reason, I can only see my pointer if I'm in the pointer mode, which I guess makes sense. And so this plus omega n kept with Q2. Okay, so basically, you take configuration, then you look at two cubes that do not overlap, right? And then in the limit, the sum of E computed on these two cubes separately and together is the same, okay? So now there's another thing to this, we can discuss it later. Why are we asking that the sum of E on the cubes is the same as E on the union? Okay, so maybe we can, maybe we can ask that it's not the sum that is the same as E on the union, but it's maybe maximum of these two guys, something like that, or some other function. So that's something that actually has been considered, but we're not going to go into that. And finally, this C and C is probably the most natural so far, right? Well, if you don't count short rangeness. So if you have a cube and you have a set that's really close to it, then the asymptotics do not vary much. So it's pretty close to the asymptotics of the cube. So for any approximation, so however you want to approximate asymptotics from the cube, if you take a big enough set inside it, you get roughly the same value asymptotically. So that's what C is asking for. And so this is going to be true if the kernel is continuous when points are not overlapping. Right? So for example, for these kernels, this is certainly true, and for optimal quantizers and so on. So this it's quite natural. And so what is the conclusion of all these beautiful assumptions? Well, the conclusion is that you can tell what the rate is up to some slowly varying factor. So you can determine what this W of t is going to be a power function, okay? And the monotonicity of this power function, so it's going to have exponent either here or there, and exactly where the exponent will live depends on monotonicity of this guy. So either this asymptotics was increasing with the size of cube, so bigger cubes mean bigger asymptotics, or bigger cubes mean smaller asymptotics. So then depending on that, you'll have different place for sigma. But the idea is that W must necessarily be power function. So somehow everything that we have discussed so far is complete, right? So the only thing you can get, if you look at the short range interaction, is something that has rate equal to a power function, effectively, up to maybe some log factor and so on. Secondly, you can compute asymptotics, and asymptotics is going to be, value is going to be constant divided by the Lebesgue measure of A. So basically, asymptotics only depends on the Lebesgue measure of the compact set that you're looking at. And so far, we don't have weight, but in general, everything works for weights as well. And you can also determine the weak star limit of these optimal configurations. So basically, the moral is that if you know behavior in cubes, if you know that things far apart do not interact much, and there is some stability, right? There is some continuity, so that if you perturb set a little bit, things don't change much. Then you know everything for any compact set, and you also know the limiting measure, and you know the rate. So you can basically recover everything in a single formula. So you recover all the previous cases. And so yeah, so something that I already mentioned. So sigma is going to be determined by how E scales. Right? So I said that you need asymptotics on the cube, and that mostly follows from scale invariance. And so if you know how E scales, you'll know exactly what sigma is. So you can also add weight, and you get the same formula. So there. So asymptotics is given by the same formula, and you see that this is just this one expression, not two. And so optimal quantizers correspond to sigma equal to minus 1 plus P over D. And for these energies, you'll have sigma equal to S over D. And so everything works, everything goes through. Now, another thing that you can do with this is that you can obtain an analog of the discrete interaction, right? So previously I said that we have this hypersingular case where S is bigger than D, and so it doesn't make sense to look at the integral. The integral will diverge in that case. So now, once you know the asymptotics, you can introduce an analog, a continuous functional that corresponds to the limit of discrete functionals. So the way you do it is you take these interaction functionals, right? They act on discrete configurations, but what you're going to do is you will lift them to any measure just by putting e to be plus infinity elsewhere. And then you just look at this asymptotics. Now this is asymptotics for functionals, not for not for numbers. Okay, so these are not numbers. This is a functional, and you're just normalizing it. So what the moral of this is, you get some continuous analog of the discrete problem, right? So for the long range case, okay, so you had long range case, and there the continuous analog was, just, so say for the Rees kernel, it was just this expression. So it was a double integral. Now for this guy, it's no longer a double integral, it's a single integral. And that's basically the reason why you can compute limiting measure. So you now have a functional which not computes a double integral with respect to it, but the functional takes a measure and it evaluates this thing. So if you have weight, you have to multiply things by weight. You just compute the density with respect to Lebesgue measure, and you evaluate this integral. Okay, so this is the continuous analog to the discrete problem, such as, so this to the discrete problem is the same thing this integral is to the double sum in the long range case, in the integral case. And so the nice thing that follows from this is you can immediately see what the minimizing measure must be. You just do a variational argument with this function, with this integral. And you will see immediately right away what the equilibrium measure must be, because this is the gamma limit of the discrete functionals. And so minimizers of the discrete guys will converge to the minimizer of the continuous guy. So this sort of right away illustrates that, okay, well, there is some continuous functional corresponding to the discrete guys, and just like in the continuous case, discrete minimizers go to the continuous minimizer. And so I started with the tale of two problems, right? And I said that the two problems were optimal quantizers, Rees interactions, and then there is another problem that you can talk about, which is the person-strang meshing algorithm. Now that makes three problems. So we have three problems: optimal quantizers, Rees interactions, person-strang meshing algorithm, and actually you can talk about quadratures. Optimal quadratures fall into the same framework. And so that's four problems now. So I guess at this point, really no one expected the Spanish Inquisition. I think I'm a little bit short on time. So do I have 2 minutes?
Yeah, you have 2 minutes.
Okay, so 2 minutes it is then. So basically, I'm just going to give you an idea of what can happen next, right? So these two types of problems, quantizers, Rees interactions, are not the only way people have been generating distributions, right? If you look at meshing literature, there are papers with thousands and thousands of citations. What they're doing, they're generating meshes. They're not generating meshes out of the blue. They're generating them on points distributed according to some density. So how do you distribute points according to some density? Right? Clearly, if you're not going to try to use long-range interaction to do that, because for long-range interactions, it's hard. So my suspicion is, whenever you look at the meshing literature and you see something that generates a distribution that you want it to, it's a short-range interaction. And so here, since I have very little time, I'm just going to tell you what the idea is. They throw in points in the set, they look at Delaunay triangulation, and then they pretend that the edges in the Delaunay triangulations are little springs. Okay, they're springs. They will repel your points, and then they move these points so that to reach equilibrium, and they retriangulate on every redo the Delaunay triangulation on every step, and then they reach these nice configurations. So basically, I'm just going to skip exactly what's going on there, but you can do the same construction for this interaction. They introduce it as dynamics. You can integrate the dynamics and come up with the nice, beautiful expression for oh, this 1/2, by the way, should be here. Okay. Well, whatever. Certainly makes it much easier that way. So you can come up with something that you can see is A, scale invariant, and B, it's short range, right? So far apart points do not interact much. And so you can establish similar results. You can establish asymptotics and so on. So this leaves us with a bunch of open questions, right? So what other things are there that are short range? Okay, so the short rangeness is maybe hiding in more places than we think, because, for example, if you look at the second term for the Rees energy, it's a little bit like short range. At least the density is just right. Okay, so the density looks exactly as if it were a short range interaction. So is it actually, in the sense of this definition that we give previously, is it somehow a short range interaction for the purposes of asymptotics? Probably. I don't know yet. Then there are some things that I'm also sort of that stood out for me. So for point distribution, for Rees minimizers, for all these configurations, we talk about the limiting distribution, right? So, but we don't talk about the structure of, say, Delaunay meshes. So there seem to be some interesting theorems about bounding the degree of the Delaunay mesh. So basically, find a Rees minimizer, triangulate it. Is it true that the degree of every vertex is bounded independent of the cardinality of the minimizer? So this seems to be true because all these meshes, they only work because something like this is true. But there are no theorems about it. So there are theorems about the maximal degree of Delaunay triangulation for a random configuration, not for a minimizer or some functional. So that would be really interesting to look into. And so at this point, I probably have exhausted your patience altogether. So I think I should stop.
Well, let's thank the speaker. Do you have any questions? So I had a question, and maybe this is something you might have addressed and I missed it, but if you worked on like manifolds and were using geodesic distance raised to some kind of negative power sufficiently large enough, do you think similar results might occur there, or?
I think so, yes. Yeah, so for large n, yeah, that's so maybe you need some sort of bound on the exponential map, right? So I mean, when you introduce some atlas on this manifold, maybe you need some control on the norm of the Jacobian or something like that. But it's probably true. Yeah, probably true. So so there was something that I skipped, but people do these outrageous things where they introduce bubbles, and they do these very nonlinear interactions. They look a little bit like Leonard Jones or something, and still they get them to converge to the right distribution. So the engineering ingenuity is boundless. So the question is just how we prove theorems about these things. Yeah, so as long as it's short range, right, and it's possible to get some asymptotics in the flat case, then yeah, I think it's going to be true with embedded distance as well.
Other questions for the speaker? All right, well, I will stop the recording here.